Hello viewer, this is Elimu TV. I'm your teacher Benjamin Makanda. I invite you to Form 3 Chemistry lesson, and today we want to continue our discussion on gas law, and our focus is on Graham's law of diffusion and the rate of diffusion. So we are saying that we are doing Form 3. So we are doing Graham's law of diffusion, and I was saying, if you can recall from what we discussed in our previous lesson, is that we were able to define what diffusion is, and we said diffusion is the movement of particles or molecules from a region of low concentration to a region of high concentration. And we used the demonstration of potassium permanganate placed in water. You can just have a revisit this. We have it here. So we have the first setup. So this setup A, then we have setup B here. So we have water. This is colorless, and then we have purple color. So initially the potassium permanganate here was purple in color, but after a while the color of the solution turns purple in the entire solution. This is because the particles of potassium permanganate have moved from a region where their concentration is high to a region where the concentration is low, and that's what we are calling diffusion. So that's the first demonstration that we discussed in our previous lesson. So we also looked at diffusion in gases. This is an example of diffusion in liquid. We also had a demonstration of diffusion in gases, and in this case we used two gases. So we have a setup. Now, this end, let's call this end A, then this end here is end B. This end A, we have solution of ammonia. So we have cotton wool soaked in solution of ammonia, and then here we have cotton wool soaked in solution of HCl, hydrochloric acid. Now, one thing that we have to note here is that both ammonia gas in solution and HCl here, they are volatile. And because they are volatile, they will be able to actually change into gas and be able to move. Now, the rate at which ammonia gas move and the rate at which hydrogen chloride gas is going to move at the other end, they are different. And their difference is in reference to their relative molecular masses. Whereas the relative molecular mass of hydrogen chloride gas is equals to 1, that's the RAM of hydrogen gas, plus 35.5 for chlorine to give us 36.5. The RAM of ammonia at this end is going to be 14 for nitrogen plus 1 times 3 for hydrogen, which gives us 17. Now, from our working, you realize that ammonia gas is less heavy as compared to hydrogen chloride gas. As a result, the molecules of ammonia will move more faster as compared to the molecules of hydrogen chloride gas. So within the tube, when these molecules are moving, you note that they are going to meet at a point marked X within the tube, and this point marked X is closer to the end B where hydrogen chloride gas are, meaning that the molecules of ammonia are moving much faster than the molecules of what? Hydrogen chloride gas. So this demonstration here tells us that actual diffusion takes place in gas. So at the point where the two gases are meeting, where I've indicated using the cross here, we have the formation of a compound called ammonium chloride. And how do you tell that ammonium chloride has been formed? We are going to have the formation of dense white fume. We will have the formation of dense white fume, which indicates that the two gases have actually met, and they meet close to the end where we have hydrogen chloride gas. Now, this one tells us something about the rate of diffusion of gases. The rate of diffusion of gases is inversely proportional to their relative molecular masses or the density of the molecules of those particular gases. So that if ammonia and hydrogen chloride gas are diffusing in the tube, then what is formed that can tell us or can help us explain the rate of diffusion? We write the equation of the reaction of ammonia gas reacting with hydrogen chloride gas, and this one gives us ammonium chloride solid. This is a dense white fume that is formed within the tube, and this one indicates that the two gases have actually met. And I'm insisting here that the ammonium chloride solid that is formed is towards that end that is near hydrogen chloride gas, simply because ammonia gas diffuses much faster than hydrogen chloride gas. Having said that, then how do we quantify the rate of diffusion of gases? This again is just a revisit of what we discussed in the last lesson. We say, according to Graham's law, the rate of diffusion of a gas, is inversely proportional to the square root of density of that gas. The square root, of density of that gas. The rate of diffusion of any given gas is inversely proportional to the square root of density of that particular gas. So the rate of diffusion of hydrogen chloride gas or ammonia gas is inversely proportional to that. Now, we can also say that, or rate of diffusion is inversely proportional to the square root of molecular mass. I will use M. Rate of diffusion is inversely proportional to the square root of molecular mass. So let us compare the rate of diffusion of ammonia and hydrogen chloride gas in this case. So how do we compare? So we say, let R stand for the rate of diffusion of ammonia. So rate of diffusion of ammonia, R, divided by the rate of the, rate of diffusion of ammonia equals, I introduce the equal sign, equals to constant over the square root of molecular mass of ammonia. This is my equation number 1. So that if I rearrange this equation to make the constant the subject of the formula, then the rate of diffusion of ammonia gas multiplied by the square root of molecular mass of ammonia is equals to constant. Then the rate of diffusion of hydrogen chloride gas is equals to constant over the square root of molecular mass of HCl. So if we rearrange this, we'll have the rate of diffusion of HCl multiplied by the square root of molecular mass of HCl, which gives us a constant, and this one becomes our equation number 2. That one becomes our equation number 2. Now, we want to combine the two equations. You realize in the two equations, they both have constants. This means that the constants are the same. Therefore, say the rate of diffusion of ammonia multiplied by the square root of molecular mass of ammonia gas is equals to the rate of diffusion of HCl multiplied by the square root of molecular mass of HCl. Are you together, class? Because in both cases you are getting a constant. So the rate of diffusion of ammonia gas multiplied by molecular mass of ammonia is equal to the rate of diffusion of HCl multiplied by the square root of molecular mass of HCl. Now, let's we divide through here by the square root of molecular mass of ammonia. We divide here by the square root of molecular mass of ammonia. So if we divide that way, we are going to have this and this cancel out. And then here we come divided by the rate of diffusion of HCl, divided here by the rate of diffusion of HCl. So these ones and these ones cancels. So what is left? We have, therefore, the rate of diffusion of ammonia over the rate of diffusion of HCl is equals to into the square root of the inverse of the molecular mass of HCl over the inverse of molecular mass of ammonia gas. So this is how we compare the rate of diffusion of the two gases. Now, let us compare the rate of diffusion of these two gases. If we have already had this, we can now substitute. So the rate of diffusion of ammonia gas over the rate of diffusion of HCl is going to be equivalent to into the square root. The molecular mass of HCl was found to be 36.5. Then the molecular mass of ammonia is 17. So if we work out this, we will get this. So the rate of diffusion of ammonia gas over the rate of diffusion of HCl is equals to, work out this value and the square root, you will get 1.465. You work out and get it as 1.465. So making the rate of diffusion of ammonia gas the subject of the formula, you will have something like this. You will have the rate of diffusion of ammonia gas is equals to 1.465 times the rate of diffusion of HCl. This means that the rate of diffusion of ammonia gas is 1.5 times faster, 1.5 times faster the rate of diffusion of HCl. So we are able to compare the rate of diffusions that way. So if you have to interpret this one, this means that the rate of diffusion of ammonia gas is 1.5 times faster than that one of HCl. Ammonia gas diffuses 1.5 times faster as compared to that one of HCl. So you now understand how we can be able to compare the rate of diffusions of gases and how we can be able to demonstrate the rate of diffusion of liquids. In our next lesson, we will be looking at the problems that can be used to work out the different rates of diffusions of various gases. So up to there, I hope you have enjoyed your lesson. I've been your teacher, Benjamin Makanda. Until next time, stay tuned to the TV. Thank you.